Hello once again, and welcome to the Cornish Radio Amateur Club series of slide videos for the RSGB Advanced Certificate. And today we're going to continue our look at receivers, and this slide video is entitled Receivers D. And it builds on Receivers A, where we looked at characteristics of the receiver, the 6 key features that we want in a receiver. Receivers B, when we looked at the superhet receiver. Receivers C, when we delved into more of the circuitry within the blocks in the block diagrams that we've been looking at. And here in receivers D, we're going to have a bit more of an in-depth look into some more aspects of superhet receivers, including IF amplifiers at AGC, but with a particular emphasis on demodulation. So receivers D is all about converting the signal that's coming in into audio. So we're going to look at different types of modulation. We're going to look at AM and how to detect AM, FM discriminators, how to turn an FM signal into audio. We're going to look at SSB, and we're going to have a little look at noise limiting. So let's see how the signal got to the receiver in the first place. Let's remind ourselves of the generic transmitter block diagram. And here you have the block diagram once again, with the microphone on the left and the antenna on the right. So the signal is, if you like, travelling from the person's head on the left to the antenna on the right. And if we have an audio signal, and remember audio signals are typically between 300 Hertz and 3 kilohertz, 3000 Hertz in the audio amplifier. And we mix this with a frequency from the frequency synthesizer, or that could be simply a crystal oscillator if it was a single frequency transmitter. For AM modulation, we'll end up with an envelope after the filtering's taken place of something like that. Now that AM envelope should be fairly familiar to you by now. It is essentially the carrier frequency changed in amplitude by the modulating signal, which is coming from the voice. So now that we've got our envelope, let's have a look at the superhet receiver. Well, the target is to get audio out of the speaker, and the audio to be as close as possible to the audio that was originally encoded as modulation on the transmitting signal. So let's take an example. Let's assume there's an envelope coming in with a 7 megahertz signal. And I should point out that that would be not in conformance with the band plan, so these frequencies are just for illustration. If we chose a scheme where we took the difference frequency, F1 and F2, then the local oscillator would be at 6.53 megahertz if we had chosen an IF of 470 kilohertz. So to go through that another way, if our receiver has a scheme with a local oscillator that tracks below the signal frequency and a 470 kilohertz IF, then for a 7 megahertz signal, the local oscillator would need to be tuned by the operator to 6.53 megahertz. And from receiver C, I think you should find that a fairly familiar concept. Let's have a little look now at that signal coming in, the 470 kilohertz signal, and break it down into its bits and pieces. So there it is, an AM signal, an AM envelope, and if we look at the frequency of the IF, 470 kilohertz, It's got a period then of 1 over f, and that's about 2 microseconds. We should be able to calculate that fairly readily. Now we need to send that to the detector, and the output of the detector needs to recover the original audio. And in this example we had a 2 kHz tone. And the 2 kHz tone, which is roughly mid-band of voice, would have a period of 0.5 microseconds. Or, sorry, correction, it would have a period of 0.5 milliseconds or 500 microseconds. So let's have a look at how we go from the top waveform, which is essentially an amplitude modulated signal centered on 470 kHz, to the bottom waveform, which is a 2 kHz tone. Obviously, in real world examples, we probably wouldn't be sending a tone, but sending a complex waveform for voice. But the tone serves to illustrate the point very well. So let's look at the mechanism from going from the top waveform to the bottom waveform. Well, here is the beginning of the diode detector. We've covered in the intermediate course, and I think a little bit in the foundation course, the concept of using a diode to detect AM. So the transistor then is the final transistor of the IF amplifier, and that going into an IF transformer. We've also had a look, I think in Receivers C, at coupling of IF transformers. So there we have an IF transformer, which is an effective filter, and it's passing on that signal, which is centered on 470 kHz in our example, and is amplitude modulated. If we add a diode and a resistor to the circuit, the diode then has the effect of rectifying the signal from the IF, and I've shown that there in red. So the output at this stage would look something like that. The negative half cycles would have been blocked, or if you like, not conducted by the diode. But at this point we still have an envelope with a fundamental frequency of 470 kHz, and although it is still amplitude modulation, but only the top half has got through. If we connected that to an amplifier, an audio amplifier or a speaker, we wouldn't get any meaningful results, because audio amplifiers have responses between 300 and 3 kHz, not around 470 kHz. So we need further components then to completely convert this to audio. And the answer is that we need a capacitor. When we connect the capacitor then on the circuit, and if the CR, the time constant, is somewhere around 200 microseconds, that's the example used in the RSGB book Advance, then we will recover the envelope rather than the IF frequencies. Because what will happen is that the IF frequencies will be, if you like, filtered by that RC filter, leaving the envelope remaining. And so that's what we have there. Now you might say, well, what sort of values would you need for CR, and how would you actually choose an appropriate CR for a circuit? Let's have a little look at that now. Let's see how we might choose a suitable time constant without actually doing the calculations, but looking at the implications. So if we zoom in and have a look at the last 4 spikes or half cycles of our envelope, and we examine these in a bit of detail in the context of our detector circuit, which is up there on the right. If we choose our time constant ideally, then the output signal, the audio, will exactly track the peaks of our envelope. And then we'll have zero distortion, at least from what we had in to that circuit. If we make our time constant too long, there won't be enough time between the half cycles for the capacitor to discharge through the resistor, and so gradually the capacitor will hold its charge in excess of the peaks of the half cycles, and we'll get something like this. And the gap between the ideal time constant and the excessively long time constant will manifest itself as distortion. On the other hand, if we select a time constant that's too short, between the half cycles, the capacitor will discharge excessively through the resistor, only to have to recharge when the next half cycle comes along. And we'll end up with a jagged top to our waveform. And once again, this will represent a distortion. Now, we don't have to worry too much about the time constant, and in fact you don't have to worry about this at all for the exam, but it's simply to illustrate the function of the functioning of the amplitude modulated detector, the diode detector. And we don't have to worry too much about the time constant, because we just have to get it so that it's suitable for the audio, but shunts, if you like, or filters the IF. And as there's such a difference in frequency between the top frequency, 3 kHz of the audio, and the 470 kHz of the IF, that shouldn't be a problem. We don't really have to worry too much about the differences between 300 kHz and 3 kHz, because that's not going to make a huge difference. Let's have a look now at amplitude, at automatic gain control, AGC. There we are, reminding ourselves of the super heterodyne receiver. And after the IF amplifiers, we should have a envelope, amplitude modulated IF, with an envelope that looks something like that, which goes through a detector and comes out of the speaker at something like the blue waveform shape. And there I've shown an envelope with considerable, perhaps exaggerated amplitude, and that will produce a loud noise out of the speaker unless we quickly adjust the audio amplifier. On the other hand, if I had a small signal or a small amplitude variation into the detector, that will result in a small amplitude variation coming out of the speaker. Now, with the variable nature of radio, and particularly HF, we might find ourselves having to constantly adjust the audio frequency gain, and we would also find it difficult to keep our signals within the centre of the dynamic range of the IF amplifiers. So some sort of automatic control is warranted. And on the classic superhet diagram that you see in the RSGB book Advance, it shows a feedback loop from the detector to both IF amplifiers. And let's have a little closer look at the functioning of that feedback loop. Well, here we have an AGC. There is the final IF transformer from the previous stage, and we should be familiar with that. We've had quite a good look at IF transformers in the context of IF amplifiers. This part of the circuit, highlighted in yellow there, should also be familiar to us. We've just covered it. It's the diode detector with a diode and a C1R1, and we've just discussed choosing C1R1 to best effect. So we've got some additional parts to this circuit now. Here we have one of the AGC lines. You remember in the previous block diagram of the classic superhet, we had the diode detector feeding back two AGC lines, one to one IF amplifier, the first IF amplifier, and one to the second IF amplifier. So this would be a way then, with the highlighted circuitry, to pick off the received signal, convert it into a control voltage. Now C2R2 there would be chosen with completely different time constants to C1R1 in the previous example, because we're trying to provide variation over not individual cycles of speech waveform, but perhaps over a few seconds or half seconds or something like that. So the time constant C2R2 would be far longer, and that would provide a DC control voltage back to a previous IF amplifier. And similarly, C3R3 in conjunction with D3 would do the same thing, but at a different polarity. And how these circuits would be designed would depend on the IF amplifiers that they were being connected to. Let's pull things together a little bit. There's our circuitry, and here we're adding in an IF amplifier. And you can see that that was an example, I think, from receiver C, where we looked at the circuitry within the blocks, and that was an IF amplifier. And you can see then that the highlighted, the red AGC control line there, going back and affecting the base bias of that NPN transistor, and therefore the gain. So that covers AGC, I think, certainly to the extent required by the RSGB Advanced Certificate. Let's go on now and look at demodulating FM. There is our rather more complicated double superhet. We've seen this diagram before, and if you look over onto the right hand side, we have covered the envelope detector for AM. We have now to look at a way of detecting FM. So we're looking to find an FM discriminator, and the particular example used in the RSGB course is the ratio detector. There are other detectors, the Foster-Seeley, etc., but it's a ratio detector that's been singled out for special attention. And the advantages and disadvantages of the ratio detector you can find in the book. One of the advantages is it's fairly immune to amplitude changes. What we want in a detector, an FM detector, is it responds to FM changes, but if the incoming signal varies, perhaps due to propagation or other factors, we don't want that being superimposed on the audio. So the ratio detector has a fairly good tolerance, let's say, for amplitude changes while responding well to frequency changes. So let's have a look inside the block there and see what's going on. So here we have an example ratio detector. Now the operation of this is not exactly intuitive, and I'd advise you to have a look at the book, but essentially it goes something like this. There is the final IF transformer, and there's an extra winding there, L1, on the secondary. This induces phase changes at the points there marked A and B. So as at center frequency there, the voltage at A is the vector sum the voltage out is the vector sum of the voltage at A and the voltage at B. So the VA vector is shown there, and the VB vector is shown there, and V1 is the resultant. And that provides equal voltages, V1 and V2, which are across the capacitors C1 and C2. However, if we move below the centre frequency, we get a phase shift at A, and so the vectors become unbalanced, changing the resultant voltage. So the resultant then is changing in amplitude as the incoming frequency changes in frequency. And with this happening, it's detected then by the diodes D1 and D2. This provides an audio output. Now, if we have a look at the circuit, there is another graph there of its usable range. If we go up too much in frequency, then the tuned circuit, we move outside of the bounds of the tuned circuit and the performance drops off. And similarly, if we go down too far in frequency, the same thing happens. So we need to be working around the top peak of the tuned circuit and a little bit either side of it, but we can't be working in the skirts, and that is what this is showing, this graph down at the bottom, showing the discriminator output. So the main points to remember then for FM discrimination with a ratio detector: it's got fairly good immunity to amplitude variations, that changes in frequency induce changes in phase in the transformer, and these changes in phase result in currents flowing, which then have the effect of changing frequency changes and phase changes into amplitude changes, and these amplitude changes are the resulting audio. Let's look at the next part of demodulation. We've covered AM demodulation with the envelope detector. We've now covered FM demodulation or discrimination with the ratio detector. We're now going to have a look at these two blocks here, specifically the product detector at the top. And the product detector works in conjunction with a carrier insertion oscillator. Now you will recall that SSB is a single sideband where we have stripped away the carrier and the other sideband. So sometimes we're sending just the upper sideband, or sometimes we're sending just the lower sideband. And you will recall from the video on transmitters, this gives us considerable advantages in terms of the fact that we can concentrate our power allowance or our power capability into just the information carrying part of the signal. We don't have to send the redundant parts. And by redundant part, I mean the carrier and the other sideband. So let's have a look inside the product detector. But first of all, let's have a look at the spectrum of speech. Now here we have a chap speaking to a microphone making a sound, and we're looking at the result on a spectrum analyzer. And the output waveform will look something like that. Remember that on our journey through the electronics associated with amateur radio, we tend to look at two types of waveforms visually. One is from an oscilloscope, and remember that the x-axis on an oscilloscope is time, and the other one is on a spectrum analyzer, and the x-axis on a spectrum analyzer is frequency. The y-amplitude in both cases, the y-axis rather, in both cases is level or amplitude. So here we're looking at a spectrum analyzer display, and we're looking at the voice components of the person speaking between 0 and 3000 Hertz. And you can see there 3 distinct peaks somewhere below 1 kilohertz in this particular example, and then other peaks occurring as he makes that continuous sound. Now, we can't predict what these are going to be like because speech produces complex waveforms, mixes of frequencies, etc., but this will give a general impression of what it might look like. Now, as we pass this waveform through various stages of mixing, sometimes it can become inverted. And here's an example of what happens. Here the speech on the left, that is erect, and the same one as I showed you a second ago in the previous slide. But due to mixing, and we'll go through this in a minute, it's become inverted, if you like, folded over, or a mirror image. So the top frequencies now are at the bottom, and the bottom frequencies are now at the top. Now, it's useful to have a way of representing this as we go through block diagrams of transmitters and receivers. And so we use a symbolic representation. It's something like this. The sidebands then are shown erect with the triangle on the left and inverted with the triangle on the right. And if we look at them, some people leave a small gap between the center frequency, perhaps the carrier frequency or the IF frequency, and the beginning of the waveform at 300 Hertz, because, as you recall, voice is between 300 for amateurs anyway, 300 and 3000 Hertz. So some people use that representation. Some people simply don't bother with leaving a gap between 0 and 300, but use a representation like that. And either is valid, and it's simply a matter of preference. And you will see both in different publications, and in the RSGB Advance they tend to use this representation. So how would we, for example, represent an AM waveform? Well, we would represent it with its carrier, and we would then add on to the carrier the 2 sidebands. And on this representation I've left a small gap there to show no frequencies being transmitted between 0 and some lower limit, perhaps 300 Hertz. And if we looked at that then, the audio waveforms, you can see that the top or erect sideband going between 300 and 3000 Hertz, and the bottom one between 300 and 3000 Hertz, but that is inverted. If you had a single tone being transmitted, perhaps at 2 kilohertz, you might represent it like that. So that's an example of using that notation for an AM signal. And if you wanted to continue on and say, well, how would it look at the 500 Hertz, and perhaps close to an IF frequency, well, you could simply subtract and add the frequencies from 500, the audio frequencies on this AM example, as shown in the green triangle, the green boundary. So let's see what happens when we get sideband inversion and how it occurs. You'll recall then that this is the superheterodyne classic single superhet block diagram, and here we've chosen an IF of 465 kilohertz, and we've said that our local oscillator tracks high. That means it's going to be tracking above the signal frequency. So let's take an example then where we take 7.001 megahertz coming in as the nominal center frequency that we're receiving. Now this is the same example in the book Advance, and so you can work through the example then from the book as well. So if the local oscillator tracks high and the IF is 465 kilohertz, then our local oscillator needs to be tuned to 7.466 megahertz, and we will select the difference frequencies, F1 minus F2, to get, or F2 minus F1 in this case, to get 465. And you would expect, or you might expect, that the upper sideband shown coming in would be translated at IF to an upper sideband. But in fact, that is not the case. It is in fact translated to an inverted sideband. So we thought the sideband would be erect at that point, but it's going to be inverted. And let's look and see why that might be the case. How did the erect sideband coming in from the antenna become inverted at the IF amplifier? Well, let's look at those boxes a bit more carefully. If we look at the incoming signal, 7.001 nominal frequency, we can put a little yellow pin there to mark where it is. And if we take the 7.001 and take it through the mixing stage and see where it ends up, then it'll be the local oscillator, 7.466, minus 7.001 is equal to 465. So we can put a pin in at 465. So those 2 points then are equivalent. The 2 yellow pins at 7.001 and the IF frequency, the spot frequency of 465. Let's now have a look at the other end of the erect sideband coming in from the antenna. That'll be 7.001 plus, there's the point there, that'll be 7.001 plus the 3 kHz maximum frequency that we've got. So that will be 7.004. And let's track that through the mixing process. That'll be 7.466 MHz, our local oscillator frequency, minus the 7.004, and that will turn out to be 462 kHz. So then we can put a little yellow pin in, a little mauve pin, a mauve pin into the diagram, and we can see that yes, the sideband certainly seems to be inverted, because compared to how it came in, the pins are reversed. It comes in as yellow and then mauve, and then it ends up as mauve and then yellow. We can repeat this process with 300 Hz if we want. It's unnecessary, but for an exercise we might say, well, 300 Hz, it would be 7466 MHz minus 7.0013 MHz is 464.7 kHz, enabling us to put the pin in the diagram at the IF. So using this methodology, using the nominal frequency, or the bottom of the sideband, and the top of the sideband, and the extents of the sideband, we can calculate them by taking them through the mixing process and seeing where they end up at IF. And once we've done that, we can decide whether the sideband is erect or inverted, or if it was inverted coming in, has it become erect or remained inverted. So I don't think it's necessarily important for the advanced exam to be able to work these out, although we'll have to look at some example questions to make sure. But it is important to be able to understand the principle that when you go through the mixing process, sidebands can be turned the other way up. So let's have a little look at demodulating SSB then. We said we're looking at the product detector and the carrier insertion oscillator, and we now understand the notation for showing erect and inverted sidebands. So let's dig into the product detector itself. And remember, the product detector works in conjunction with the carrier insertion oscillator. And the carrier insertion oscillator is, if you like, adding the bits that were stripped away during the transmitter process, the carrier and the other oscillator, which make it difficult then for us to be able to detect the signal in an AM sort of a way. So there we are. Looking in there, this is the example given in the book Advance, and it's an FET product detector, and you can see on the left from the IF amplifier going into the gate of the FET is the IF signal. Coming in from the bottom, from a block, is the carrier insertion oscillator, and coming out on the right hand side is the AF signal. So then the product detector here takes the IF, mixes it with a carrier insertion oscillator, detects it, and gives us AF. Let's strip away the unnecessary detail. Okay, and there I've highlighted in red the carrier insertion oscillator feeding a signal in. Let's take the example that we had before, where we had a 465 kHz IF, okay, and we ended up with an inverted lower sideband coming in. And if that's the case, we need our carrier insertion oscillator to be set at 465 kHz again. So what we're trying to do then is mix a central frequency of 465 kHz with an inserted signal of 465 kHz, and the differences that we're going to get out, the products that we're going to get out from this mixing process, is just going to be therefore the audio. So we've shifted 465 by 465, and the only variation we've got then is the audio. Let's track it through. So on the box on the left, we've got what's coming from the IF. The carrier insertion oscillator will always be 465 in the box in the middle, and the box on the right then is the resulting audio. So there we are, repeating what we have on the diagram above. There's our inverted lower sideband centered on 465 but going below it in frequency. And the audio then, as a result of this mixing, will be the carrier insertion oscillator minus the IF. So if we use our pins method again, the 465 will translate once again to the 465, but to the 0 Hertz, because 465 minus 465 will leave 0. So the bottom end of the sideband will be 0 Hertz. If we look at the top end, then that will be 462 kilohertz. In other words, it'll be 465 minus the 3 kilohertz maximum frequency that we can transmit. And the 462 will be then put into the sum there, so it'll be 465 kilohertz minus 462 will be 3 kilohertz. So the pin for the audio will go in there, and there we have our audio output from 300 to 3000 Hertz. And that is the result we wanted. Now this is discussed in quite some detail in the advanced book, but there are a lot of numbers around and it can be a bit confusing. So I'm going through these simple scenarios, which I hope will help you understand, but it should be read in conjunction with the advanced book. So let's have a look at another example then of this. Let's say that not only did we have the lower sideband coming in, but we had the upper sideband coming in as well. And this might be coming in as an interfering signal. It might be another transmission from another radio amateur, or whatever. But I've put it in red as it's the undesirable signal, the one we don't want to come through to audio. We've chosen to select only the lower sideband for the purposes of this example. So if we then go and track this through, and we use a carrier insertion oscillator of 465, Then looking at the red one, and using the pins method once again, we will see that the 465 will once again translate to 0, and that the 468, that's 465 plus the 3 kHz maximum audio frequency, will translate this time not CIO minus IF, but IF minus CIO. Otherwise we'd end up with a negative frequency, which wouldn't be one of the products produced. But a product will be produced of 465 minus 468. And so I beg your pardon, 468 minus 465, which will produce 3 kHz. So once again, we've produced an output, and this is undesirable. We can't discriminate between, we can't distinguish between these outputs once one is overlaid on the other, and that will come out of our speaker as an interfering sound, which is undesirable. So this implies then that where we have two sidebands, or we have a single sideband that we want to pick out, we need to have a very sharp IF filter. And quite often crystal filters are employed at IF to be able to achieve this. So there could be the shape of the filter that we need. It needs to accept the signal that we want, the wanted signal, and it needs to reject the adjacent signal. And this plays back into the discussion that we had in receivers A, where we're looking at the 6 important characteristics of receivers, and one of them, you'll recall, is selectivity. The ability to pass the wanted signal but reject the adjacent signal. And if you recall, we said that that was mainly the job of the IF. So we've covered most types of modulation. We'll look at one that remains now, Morse. And we'll use the same scheme that we've been using in the previous examples to explain it. So if we use the same demodulator and we had some Morse coming in, I've shown there a single frequency at 465 kHz coming in. Now that will be either present or not present, depending whether the distant end key is down or not down. Remember, Morse is simply the presence or absence of a carrier wave. There is no modulation, no amplitude modulation of that carrier wave other than it's present or it's not present. So if we had a look at that going through our demodulator, from the IF we could put in a pin at 465, and at the audio we could put in a pin at 0 Hz. And unfortunately that's where we stop, because there is no bandwidth to Morse per se, and we wouldn't actually have anything to listen to, because 0 Hz is not something that we can hear. So our only solution, or actually we have a number of solutions, but the solution that we have expounded in this example is to off-tune our receiver slightly. If we change the frequency of the local oscillator slightly, then the frequency that will be present or not present will change a little bit in the IF. And with that happening, we will get in the IF a small shift, and that will result in a corresponding shift in the audio tone received in the out of the demodulator. And typically we offset the transmitter by about 700 Hz to listen to the Morse tone, because that provides a pleasing tone at the output. Now with modern receivers, as it's explained in advance, when you switch to the CW mode, the display, the digital frequency display, will display the center or nominal frequency, not the frequency shifted by 700 Hz, in order that you've got an idea of where you're tuned to. So let's just go through a couple of those points again. There is our product detector for demodulating SSB. It relies on a carrier insertion oscillator. This product detector relies on the signal coming through from the IF, from the antenna, and in our example we used 7 megahertz to 4 kilohertz above, sorry, I beg your pardon, 7.001 megahertz going to 7.004 megahertz. In our example, this was translated by a local oscillator that was tracking above the signal, and that produced this sideband arrangement at IF, an inverted sideband centered on 465 kilohertz. And that went through the product detector. It was mixed again with 465 kilohertz, and it produced a audio output of 0 to 3 kilohertz. And in this representation, this symbolic representation of sidebands, I've used the same method as in the RSGB book Advance, and ignored the small gap from 0 to 3 kilohertz. So let's look at the final topic for this video, and that is noise limiting. There once again is our modulation envelope for AM, but this time in red we can see that there are some spikes, and these spikes may be caused by impulse noise from passing vehicles, or simply atmospherics that we get from time to time in HF. Maybe a distant lightning storm causing interference on the HF bands. And these spikes can have considerable amplitude and can be many times the amplitude of our wanted signal, and can therefore be very annoying because, particularly with headphones, they could cause hearing damage and make it difficult to listen to the wanted signal. So we look for a way to limit the damage caused by these noise spikes. One of the methods used is very simple. It's simply two back-to-back diodes. And you will recall that diodes have a need for about 0.6 volts forward bias before their PN junction will allow the flow of electrons. So if we put two back-to-back diodes facing different directions, anything above 0.6 volts, whether it's a positive half cycle or a negative half cycle, will be conducted away. So this has a way of clamping the voltage to 0.6 of a volt. And if we arrange it in our receiver such that our wanted signal, our modulation envelope, has a maximum amplitude of 0.6 of a volt, this is a way of eliminating anything above the maximum amplitude of our modulation envelope. So by doing this then, putting the diodes in, we're able then to limit or clip the noise spikes above the maximum amplitude and thereby cut them off. Now you can see from the illustration there that the noise spikes still remain, and particularly those emanating during a period of low amplitude, although they will be attenuated, they'll still be present. So it's not a way of actually cancelling the noise, it's simply a way of reducing the maximum effect of the noise on what we're listening to. So thank you very much again for listening to this. We have one more video to come in the series of slide videos about receivers for the advanced course, and that's going to be receivers E. And in receivers E we're going to look at the remaining topics, and the remaining topics include predominantly a look at noise and how we deal with noise in HF receivers and other receivers indeed, and also looking at DAM converters and transverters. So, thank you once again.